For the longest time, AI had this huge, almost embarrassing problem. It was completely forgetful. Seriously, it could process something right now, but it had no real memory of what happened just a few seconds ago. Today, we're going to dig into the incredible breakthrough that finally gave AI a memory.
Just think about that question for a second. For you to understand it, your brain had to hang on to the word how, all the way to the very end. You do this without even thinking, right? But for early AI, that was like climbing Mount Everest. This simple human skill was a total game stopper, and solving it was going to change everything.
So you've got this huge problem. How did the brilliant minds back then even start to tackle it? Well, they came up with a really clever idea, a new kind of neural network built specifically for things that happen in order. Like sentences or music or anything with a timeline.
They called them recurrent neural networks, RNNs for short. The idea was that as each word or note goes in, it leaves behind a little echo, a trace. And that echo influences how the network understands the next thing it sees. This whole echo chamber thing, that was supposed to be the AI's short-term memory.
And on paper, this was genius. So elegant, so powerful. But, and there's always a but, isn't there? In the real world, when researchers actually tried to use them, it just didn't work. Not for anything long, anyway. They hit a massive brick wall.
And this wasn't some minor bug. This was a fundamental flaw that haunted the entire field. It had a pretty dramatic name, too, the vanishing gradient problem. The best analogy is like shouting into a canyon, and by the time the echo should come back, there's just silence.
This game of telephone analogy is the perfect way to get it. See, for a network to learn, it needs feedback, a signal that goes backwards saying, hey, you got that wrong, adjust this way. In an RNN, that signal has to travel back in time, through every single step. And just like that game, the message gets messed up. It gets weaker and weaker until, poof, it's gone. The network literally can't learn from its mistakes if they happened too far in the past.
And this is where our heroes, Hawkrider and Schmiedhuber, come in. They knew this wasn't just some little glitch. It was the roadblock. In their own words from the paper, the learning signal would either vanish into nothing or blow up into chaos. Either way, you were stuck. It was a total dead end. They had to invent a new way forward.
Okay, so what do you do when you hit a dead end? You go back to basics. Their first idea was, well, it was almost beautifully naive. They thought, hey, if the signal keeps fading, why don't we just build it a perfect highway where it can't fade?
And they gave it this cool name, the constant error carousel. It's like that perfect echo chamber we talked about, but this time the sound literally never stops. The memory just loops around and around, perfectly preserved forever. Sounds great, right? Perfect memory. Problem solved. Except, not quite. It actually created a whole new mess.
The best way to think about it is like a single note being played on a piano with the sustain pedal held down. Forever. You can't add a new melody without it just blending into a mess, and you can't ever stop that first note from ringing out. This led to two huge conflicts. The input conflict, how do you write new information without trashing the old stuff? And the output conflict, how do you read the memory when it's constantly screaming at the rest of the network? It was just total chaos.
And this is the moment of genius, the big aha. They realized that memory isn't just about storing things. It's about managing them. You need control. You need to know when to write, when to read, and when to forget. And that realization was the birth of the LSTM.
So what do? They took their original idea, that constant error carousel, the core memory part, and they built controllers around it. They called them gates. And the club analogy is perfect. You've got an input gate acting like a bouncer, deciding who gets to come in and become a memory. And then you have an output gate that's like the DJ, deciding when to play that memory for everyone else to hear.
And here's the really clever part. These gates aren't just simple on-off switches. They are their own tiny neural networks. They actually learn when to open and when to close, protecting that core memory from all the chaos. It was an incredibly elegant solution that solved both problems at once.
All right, so the idea is brilliant. The design is super clever, but that's all just theory. The real question is, did it actually work in practice? This is the part of any paper where the rubber meets the road. Let's see what the data says.
Okay, so the results, wow. They weren't just a little better, they were a total game changer. Look at this table. You've got other methods taking what? Nearly 200,000 attempts to even get a 50% success rate. LSTM comes along and gets 100% success in less than 9,000 tries. That's not an upgrade, that's a whole new league.
And if the table didn't make it clear, this chart sure does. I mean, look at that bar for LSTM. It's just maxed out at 100%. The others don't even come close. For a problem that was considered a major headache for the field, this was an absolute, undisputed win.
But okay, that was a standard test. The real Everest, the entire reason they built this thing, was to see if it could handle those really long gaps. Could it remember something from way back at the beginning of a sequence?
And the answer was a resounding yes. Over 1,000 steps. Let that sink in. 1,000. Remember how the old RNNs would forget things after maybe 10 steps? This was 100 times better. This wasn't just an improvement. This was the home run. This was the breakthrough they had been looking for.
So, where does that leave us? What's the big picture here? Honestly, it's hard to overstate just how important this 1997 paper was. It fundamentally changed the game for any AI that had to deal with sequences of data.
I mean, the abstract of the paper itself just says it all perfectly. LSTMs could learn to bridge these huge time gaps, more than 1,000 steps, even when the data was messy and complicated. This was the key that unlocked everything for real-world applications.
So yeah, it solved the vanishing gradient problem, which is huge. But it did something even more important. It introduced this whole idea of gating, of letting a network manage its own information flow. That single concept is the granddaddy of so much of the AI we take for granted today. We're talking about the stuff that powers your phone's autocomplete, your smart assistants, language translation, you name it. So, we went from a fading echo to a perfectly managed, long-term memory. It's an amazing story of creativity and problem solving. They solved the AI memory problem of 1997. Which just makes you wonder, right? As AI gets even crazier and more complex, what's the next memory problem we're going to face? And who's out there right now about to come up with the next brilliant solution? Something to think about. Thanks for joining me on this deep dive.